Introduction to Congruences. Let us discuss definition 1. Please take a look at what is written. Let m be a positive integer. Then integers a and b are congruent modulo m if m divides their difference. Here are examples. 3 is congruent to 1 modulo 2. Here is why. 3 minus 1 is 2. 2 is divisible by 2. Therefore, according to what is written here, 3 is indeed congruent to 1 modulo 2. So, if the difference is divisible by m, a is congruent to b. 6 minus 4, 2. It is divisible by 2, so 6 is congruent to 4 modulo 2. Negative 14 minus 0 is negative 14. It is divisible by 7, so negative 14 is congruent to 0 modulo 7. 25 minus 16 is 9. It is divisible by 9, so 25 is congruent to 16 modulo 9. 43 minus negative 27, 70, is divisible by 35, so 43 is congruent to negative 27 modulo 35. Now please take a look at Theorem 1. If a and b are integers, then a is congruent to b modulo m if and only if there is an integer k such that a is equal to b plus km. Since it's if and only if statement, we will prove it in both directions. Means, first let us show that this implies this, and then we show that this implies this. So, we start with a is congruent to b modulo m. It's over here. By definition, this means the following. M divides a minus b. By definition of divisibility, this means that a minus b is equal to km, where k is some integer. Lastly, move b to the left, the result follows. So we just proved that this implies this. Conversely, suppose this is given. It's over here. Move b to the left. Done. By definition of divisibility, this means the following. M divides a minus b, and by definition of congruence, this means a is congruent to b modulo m. We are done with Theorem 1. Example, 19 is congruent to negative 2 modulo 7. 19 is equal to negative 2 plus 3 times 7. This implies this, and this implies this. Theorem 2. 3 basic properties of congruences. A is congruent to a modulo m. Property number 2. If a is congruent to b, b is congruent to a. Property number 3. If a is congruent to b and b is congruent to c, then a is congruent to c. Let us prove all 3 properties. A is congruent to a because m divides a minus a, which is 0. Property number 2. Suppose a is congruent to b modulo m. This means that M divides A minus B. By definition of divisibility, this means that A minus B can be written as Km. Multiplying both sides by -1, we get this. And now, according to what we see over here, B minus A is an integer multiple of M, means B minus A is divisible by M, which means B is congruent to A modulo M. Lastly, transitivity. Here's what is given. A is congruent to B modulo M, and B is congruent to C modulo M. This means M divides A minus B. This means M divides B minus C. Here is what we do next. Let us add this and this. Note that A minus B plus B minus C, after we cancel B, is equal to A minus C. And now, M divides this according to what is written here. M divides this according to what is written here. Therefore, by Theorem 2 from section 1.5, M divides the whole thing. Lastly, since this is equal to this, M divides A minus C. It's exactly what is written here, which means A is congruent to C modulo M. Next, please take a look at this remark. By Theorem 2, we see that the set of integers is divided into M different sets called congruence classes modulo M. For example, if M is equal to 2, this gives us two classes of even and odd integers. Here's another example. Suppose M is equal to 3. We divide all integers into three classes. Integers that give us a remainder 0, integers that give us a remainder 1, and integers that give us a remainder 2 when we divide them by 3. Next, suppose M is a positive integer. Given an integer A, by the division algorithm, we have A is equal to Bm plus R. Let us call R the least non-negative residue of A modulo M. Similarly, we know that if A is not divisible by M, we call R the least positive residue of A modulo M. So, in any case, we can call R the least non-negative residue modulo M. But if A is not divisible by M, we call R the least positive residue, means R is not equal to 0. Here's another definition. A complete system of residues modulo M is a set of integers such that every integer is congruent modulo M to exactly one integer of the set. Here's what we mean by that. Consider modulo 2. These three sets are complete systems of residues modulo 2. These are three examples out of infinitely many examples. Here's why. Any integer is congruent to either 0 or 1 modulo 2. Any integer is congruent to either 1 or -2 modulo 2. any integer is congruent to either -7 or -10 modulo 2. Now let us consider modulo 3. These are complete systems of residues modulo 3 because any integer is congruent to either 0 or 1 or 2 modulo 3. Any integer is congruent to either 1 or 2 or 3 modulo 3. Any integer is congruent to either -5 or -3 or 23 modulo 3. However, this is not a complete system of residues modulo 3 because there are infinitely many integers that are not congruent to either 1 or 2 modulo 3. Here, any integer is congruent to either 0 or 1 or 2 or 3 modulo 3. However, this is not a complete system of residues because it's written to exactly one integer of the set. Note that, for example, the number 3 is congruent to both 0 modulo 3 and 3 modulo 3. Lastly, this is not a complete system of residues modulo 3 because the number 4 is not congruent to 5 modulo 3, it is not congruent to 18 modulo 3, it is not congruent to 20 modulo 3. Folks, any questions here?
So when we're saying 20 is not congruent to 4 modulo 3, it's the same as saying 20 divided by 20 divided by 4 does not have a remainder of 3?
No. When we say 20 is not congruent to 4 modulo 3, this means that 20 minus 4 is not divisible by 3.
Okay.
Next. By the division algorithm, the set of integers 0, 1, 2, and so on m minus 1 is a complete system of residues modulo m. So guys, there are infinitely many complete systems of residues modulo m. This is the most natural complete system of residues modulo m because these numbers coincide with remainders. Also, please take a look at this lemma. A set of m incongruent integers modulo m forms a complete set of residues modulo m. This lemma explains why these are complete systems of residues modulo 2 and 3 and why these are not complete systems of residues modulo 3. This is not a complete system of residues because it has a lesser than 3 elements. We need m incongruent integers. Here we have m minus 1. Over here we have m plus 1. It is not a complete system of residues. Over here we have m. However, two numbers give same remainder. 5 gives a remainder 2 when we divide 5 by 3, and 20 gives remainder 2 when we divide 20 by 3. So this is again not complete system of residues modulo 3, despite the fact that over here we have 3 integers. Theorem 3. Suppose R1 and so on Rm is a complete system of residues modulo m. And suppose A is a positive integer that is a relatively prime with m. Then this is a complete system of residues modulo M, again, where B is any integer. So theorem 3 shows us how to come up with a new complete system of residues starting from an old complete system of residues modulo M. Think about questions.
Is there any proof for theorem 3?
In order to prove this, we use the lemma. It says M incongruent integers forms a complete system of residues modulo M. So first we'll note that over here we indeed have M integers. All we have to prove is that these integers are pairwise incongruent. So pick any two numbers here, cancel out B, and then we can cancel out A safely because A and M are relatively prime, and then we'll get the following. If, say, this is congruent to this, then R1 is congruent to R2, which gives us a contradiction. So any two numbers here are incongruent modulo M. This is the idea. Folks, any other questions?
So just to make sure, a complete system of residues modulo M, all of the elements in them are incongruent?
Yes. So please take a look once again at the definition. A complete system of residues modulo M is a set of integers such that every integer is congruent modulo M to exactly one integer of the set.
Thanks.
Next, please take a look at theorem 4. Suppose A, B, C, D, and M are integers where M is greater than 0, A is congruent to B modulo M, C is congruent to D modulo M. Then A plus C is congruent to B plus D, A minus C is congruent to B minus D, AC is congruent to BD modulo M. In short, if we have two congruences modulo same number M, we can add these congruences, we can subtract these congruences, we can multiply these congruences. Guys, this theorem tells us why it is convenient to use congruences instead of using these expressions. Very often, thanks to these three properties, and then we will deduce another property, we'll discuss corollary, and then we will discuss theorem 5, these theorems allow us to make some proofs that we discussed already in this course shorter. We will talk about it later. Right now, let us prove 1, 2, and 3. So, A is congruent to B. It's given. This means M divides A minus B. This means M divides C minus D. Here is what we do next. Note that A plus C minus B plus D is equal to A minus B plus C minus D. Just expand parentheses here and reshuffle the terms. Now, note that since M divides both A minus B and C minus D, M divides this. It's exactly what is written here. But this means, by definition of congruences, A plus C is congruent to B plus D modulo M. Proven. Similarly, if instead of using this expression, we use this expression, in short, if we replace plus here and plus here by minus here and minus here, we get the following. This is equal to a minus b minus c minus d. And now again, since m divides both, m divides the whole right-hand side. But right-hand side is equal to a left-hand side. So m divides a left-hand side means this. Okay, it's a little bit harder to prove this. Here is how we do it. Step 1, we start with the following, AC minus BD. By the way, in all three cases, in order to prove either this or this or this, we start with the following expression, left-hand side minus right-hand side. It's exactly what happened here, a left minus right over here, a left minus right over here, left minus right over here. However, there is a fundamental difference between these two parts and the last part. Over here, in order to jump from this to this, we just expand parentheses and reshuffle. Same is here. In property number 3, we have a little bit different story. There are no parentheses here. What we do is the following. Either we subtract and add BC, or we subtract and add AD. You don't have to do both. It is enough to do either this or this. Here is why. Over here, factor out C, done. Factor out B, done. Or if you prefer this approach, factor out A, done. And factor out D, done. Here is what we do next. Note that since M divides A minus B and C minus D, M divides this and M divides this. So no matter which approach you choose, this or this, M divides AC minus BD. It's exactly what is written here, means this. Done. Here's an example. 13 is congruent to 3 modulo 5. 7 is congruent to 2 modulo 5. Therefore, 13 plus 7, we add up left-hand sides, is congruent to 3 plus 2, we add up right-hand sides, modulo 5. Over here, we subtract. Over here, we multiply these congruences. Corollary. Note that if over here we set D is equal to C, note that C is congruent to C modulo M. So we can safely set D is equal to C. If D is equal to C, this becomes the following. A plus C is congruent to B plus C modulo M. This becomes A minus C is congruent to B minus C modulo M. This AC is congruent to BC modulo M. It's exactly what we have here. In short, if A is congruent to B modulo M, we can add to both sides C. We can subtract from both sides C. We can multiply both sides by C. And here's an example. 19 is congruent to 3 modulo 8. Therefore, 19 plus 7 is congruent to 3 plus 7 modulo 8. 19 minus 4 is congruent to 3 minus 4 modulo 8. 19 times 2 is congruent to 3 times 2 modulo 8. Next, suppose A is congruent to B modulo M. We can erase both sides to any positive integer power over here. Proof. A is congruent to B modulo M means M divides A minus B. Note that A to k's power minus B to k's power by college algebra is equal to this. According to what is written here, since this is an integer, by definition of divisibility, A minus B divides A to k's power minus B to k's power. It's exactly what is written here. And now let us put pieces together. M divides A minus B. A minus B divides A to k's power minus B to k's power. Therefore, by transitivity, M divides A to k's power minus B to k's power. It's exactly what is written here, means this. Another way to prove it is just to multiply this congruence with itself k times. We'll get this. Example, 7 is congruent to 2 modulo 5. Therefore, 7 cubed is congruent to 2 cubed modulo 5. Theorem 6. Let us consider the following k congruences. Each time we have same numbers A and B. A is congruent to B modulo M1, modulo M2, and so on modulo Mk, where these numbers are integers, M1 and so on Mk are positive integers. Then A is congruent to B modulo the least common multiple of M1, M2, and so on Mk. Here's a corollary. If all these numbers are pairwise relatively prime, then A is congruent to B modulo their product. So, in other words, there are cases when we cannot put here the product of M1, M2, and so on Mk. We can replace this by their product only if these numbers are pairwise or relatively prime. Here's a very simple example. Imagine that A is 4, B is 2. 4 is congruent to 2 modulo 2. 4 is congruent to 2 modulo 2. So imagine that M1 is 2 and M2 is also 2. Note that 4 is not congruent to 2 modulo 2 times 2. It is congruent modulo a least common multiple of 2 and 2, which is 2. Lastly, Theorem 7. A, B, C, and M are integers. M is greater than 0. Let us denote the greatest common divisor of C and M by D. If AC is congruent to BC modulo M, then A is congruent to B modulo M divided by D. Here is why this theorem is important. This theorem tells us that we cannot just cancel out C. Means, if AC is congruent to BC modulo M, this does not necessarily mean that A is congruent to B modulo M. Vice versa is true. If A is congruent to B modulo M, then AC is congruent to BC modulo M. But if AC is congruent to BC modulo M, this does not necessarily mean that A is congruent to B modulo M. What is true is the following. A is congruent to B modulo M divided by the greatest common divisor of C and M. Here is why. We start from this. It's over here. This means the following. M divides AC minus BC. It's exactly what is written here. Factor out C, done. So, M divides C times A minus B, which means C times A minus B is equal to M times some integer K. Here is what we do next. Let us divide both sides by D. The left-hand side can be rewritten as C divided by D times A minus B. The right-hand side can be rewritten as K times M divided by D. Note that M divided by D is relatively prime with C divided by D. Here is why. Let us go back to greatest common divisor. Over here, note that these two numbers are relatively prime. So these two numbers are relatively prime by Theorem 1 from section 3.3. Therefore, this divides this by Theorem 1 from section 3.5. And the result follows. Folks, any questions here?
So you know how you said that if AC is congruent to BC modulo M, it's not necessarily true that A is congruent to B?
Yes.
So maybe I misunderstood, but earlier, didn't you say that we could multiply both sides by an integer?
So once again, it's exactly what I said. This does not necessarily imply A is congruent to B modulo M. However, vice versa is true. If A is congruent to B modulo M, then AC is congruent to BC modulo M.
Okay, that makes sense.
So compare. This implies this. However, this does not necessarily imply this, according to what is written here. This implies this. And now, take a look at the remark. We can show that a stronger statement is true. AC is congruent to BC modulo M if and only if A is congruent to B modulo M divided by D. I say stronger because here we prove it only in one direction. Over here we say that this is actually if and only if statement. And now in particular, take a look at the corollary. Suppose C and M are relatively prime, then this, if and only if this. So this always implies this. However, this implies this only if C and M are relatively prime. Here's an example. 5 times 10 is congruent to 2 times 10 modulo 15. By the way, note that we cannot just cancel out 10. 5 is not congruent to 2 modulo 15. However, 5 is congruent to 2 modulo 15 divided by the greatest common divisor of 10 and 15, which is 5. Done. To the contrast, observe that over here 7 and 5 are relatively prime. So we can safely cancel out 7. Done. Here's another corollary. Now compare this and this. Over here we have M. Over here we have MC. Now we can safely cancel out C. But we have to cancel out C here, here, and here. Done. Moreover, this is if and only if statement. So these are cancellation laws. Theorem 7, Corollary 1, and Corollary 2. We can think about these statements as about cancellation laws. And now let us discuss applications. Please take a look at this. Prove that 10 divides this. Well, we can use common sense in order to prove that 10 divides this. Note that no matter to which positive integer power we raise 11, the last digit will be 1. Therefore, when we subtract 1, the last digit will be 0, means the number is divisible by 10. Now, let me show you how we can use Theorem 5 in order to prove this. Step 1, 11 is congruent to 1 modulo 10. By Theorem 5, we can erase both sides to 10th power. Done. 1 to 10th power is 1. Therefore, 11 to 10th power is congruent to 1 modulo 10, which means this. Now compare A with B. Note that in B, it's really hard to use common sense. We want to prove that this is divisible by 100. One can easily prove that this is divisible by 10, because no matter to which positive integer power we raise 101, the last digit will be 1, minus 1, the last digit is 0. So this is divisible by 10. But how to prove that this is divisible by 100? Well, we apply same approach. 101 is congruent to 1 modulo 100, because 101 minus 1 is divisible by 100. Now, by Theorem 5, we can erase both sides to the power 2003, which gives us the desired result. Folks, any questions here?
This is a slightly unrelated question. So the way we defined this congruence was that, for example, 101 minus 1 is divisible by 100. Can an alternate way be that 101 divided by 100 has the same remainder as 1 divided by 100? Would that work for all numbers?
Yes, absolutely. Since they give same remainder, they are congruent modulo 100. Next, find the last digit of this and this. Again, we can use common sense. It is clear that the last digit is 1. But we can use congruences. This is congruent to 1 modulo 10. Therefore, this to this power is congruent to 1 modulo 10. Last digit is 1. Same is here. So it's a pretty simple example. But now, please take a look at problem 3. Let us compare problem 3 with one of problems that we discussed before. Please compare with this. Over here, prove that 3 never divides k squared minus 2. Over here, a squared is never 3k plus 2. Note that these are equivalent problems. This can be restated in the following way. K squared minus 2 is never 3m, which means a squared is never congruent to 2 modulo 3. Note that it took quite some time to prove this in section 1.5. Now compare with this much shorter proof. Here is how we do it. By the division algorithm, each integer is congruent to either 0 or 1 or 2 modulo 3. It's exactly what is written here. A is either congruent to 0 or 1 or 2 modulo 3. Raise both sides to the second power. Done, done, done. Note that 0 square is 0, 1 square is 1, 2 square is 4, which is congruent to 1 modulo 3. So, no matter what is A square is either congruent to 0 or 1 modulo 3. Therefore, A square is never congruent to 2 modulo 3. Done. This example tells us that when we use congruences, often solutions are shorter than if we use expressions like BQ plus R. You can take a look at other examples, same nature. Prove that there is no perfect square which is congruent to 2 or 3 modulo 4. Now we consider 4 cases, square both sides, and we conclude that A square is congruent either to 0 or 1 modulo 4. Therefore, A square is not congruent to 2 or 3 modulo 4. Remember, the remainder is unique. Let us actually go over this. Prove that the following equations have no solutions in integer numbers. So, how to prove that this has no solutions in integer numbers? Or rewrite this as this, which means that x is congruent to 5, which is congruent to 2 modulo 3. This is impossible by problem 3. In problem 3, we proved that A square is congruent either to 0 or 1. Therefore, x squared is not congruent to 2 modulo 3. Compare with D. Let us discuss D. Note that by problem 4 that we just discussed, x is congruent either to 0 or 1 modulo 4. Therefore, the difference of 2 squares is congruent to either 0 or plus minus 1. But note that negative 1 is congruent to 3 modulo 4. So x squared minus y squared is congruent either to 0 or 1 or 3 modulo 4. But 2002 is congruent to 2 modulo 4. We got a contradiction.